morning. So this is the last lecture to a very short introduction to distribution theory and Sobolev spaces. As I said, it's only a glimpse of this theory, but those who are interested in studying should get into that and spend some substantial amount of time to really get the understanding of distribution theory. And of course, Sobolev spaces we don't do much because it involves a lot of technicalities. So I will just introduce a Sobolev space which is relevant to our weak formulation, which were introduced 2 to 3 lectures back. So before going to that, so distribution theory we already explained it. It's a d prime of the dual of d omega, and then we have seen some examples and all that. And before going to Sobolev spaces, this talk basically consists of 2 parts. One, I will give a existence of a weak solution, and the second part of the talk we will introduce quickly the Sobolev spaces. So this is one thing, existence of an L2 weak. I will not give all the proof, but how you see this existence of an L2 weak solution for a general linear second order operator. Not linear nth order operation for a general linear is in nth order operator. Because so what is your operator may look like this. So you have your PXD. This is your operator. So your operator is something, linear operator should look like x d power alpha. Okay, so this mode alpha is less than or equal to m, and it to be a genuine nth order operator, at least one of the coefficient of the largest term should be non-zero, such that a alpha is not equal to 0 for some alpha with mode alpha equal to m. So that precisely to make it a genuine thing. That means, so if it operates on u, is d power alpha of u. That's it. Okay, so that's what you have an operator. Here you assume a alpha smooth. So not deal. You can deal with other cases. A alphas are smooth. Okay, so and so we will do. So there are some concepts like which we don't need it here. Concepts like simple concepts like full or complete simple, because when you read other books and learn more, you will say what is called the full symbol, which is a polynomial of degree m, that's equal to sigma a alpha of x. So it is a multi-index psi power alpha, but mod alpha less than or equal to m. And there's also a notion like principal symbol. Okay, symbol. That is Pm of xi. These are all useful. May not be in this class anyway. This is a kind of a vague set of lectures. Alpha with only the highest thing. You know that even in second order you see how you use the second order to define ellipticity and all that. Corresponding to this one, so we will define what is an adjoined operator. Adjoined. A alphas can be complex. Can have that also. This is something here. Okay. So adjoined you denoted by p prime. This is not prime. P dash of xd is the same thing. It's a adjoined comes from by integration by parts. If you do that, minus 1 power of mod alpha less than or equal to m. Okay, d power alpha of So you get this alpha bar if it's a complex thing, alpha bar of x, and then if you apply to u, so this will be inside. Okay, apply to u, so you will have u here, this one. That's natural, right? When you do an integration by parts, for example, when you have a something like say f of x d by dxi of g some other phi, then it will go like this, right? If it is valid g, if you want to do an integration by parts, you will have something like d by dxi of f phi. You see, that's why. So you write down your pxt and that, but pxt is everything is given in this general setup. So you are looking for a solution. Okay, so you can study these things in advanced other PDE courses. If you look into many classical PDE, you will understand all these things. So okay, so definition: a function u in L2 of omega is called a weak solution of, there's no boundary condition or anything I'm defining here. Okay, solution of u, solution of p of xt of u equal to f if it is a solution of this equation. Okay. If u is basically p prime of xt, p prime of xt of phi equal to f phi. So there's no, so only the solution in the sense of, basically in the sense of L2 you are defining. This is true for all phi in. So basically you are understanding it as a distribution solution. Okay. So for all this thing, you have the solution is defined in the sense of distribution. That's how you define. You can interpret this in the sense of distribution. So when you integrate by parts, you get this one. So this is what your definition. And this is the inner product, because this u is in L2. So this is an inner product. This is also an inner product in L2. Okay, so you understand that. Here f is here, f is also in L2 omega. So everything is in the setup of L2 you are defining. So this is inner product in L2 of omega. What is the inner product in L2 of omega? Fg is equal to integral of Fg bar if you are working with complex thing for all Fg in L2 of omega. So this is the inner product in L2 of omega. So if you have this one, so you have a theorem. I will not give the complete proof thing. So let me give you a theorem here. Okay, this proof I will give a necessary and sufficient condition. Necessary and sufficient condition. Okay, necessary and sufficient condition. Pxd of u equal to f. Of course, you start with f in L2 of omega has a weak solution. U has a weak solution. U in L2 of omega if and only if, so this is a necessary only if there is an estimate modulus of f phi is less than or equal to some constant into norm of p prime of p prime of xt. So let me p prime of ft and L2 of omega. This is true for all f v in d omega, and c is a constant. Okay, this is what you are. So there is a necessary and sufficient condition for the existence of a L2 weak solution. So let me give this necessary and sufficient condition. So to prove this existence, so you look for operators for which this condition verifying is enough. So let me give proof of this, and then we will go to the Sobolev space, and then I'm just after making a comment. So assume one way. So we will prove that. Assume U is a L2 solution. Assume U is a L2 solution. Then what we will get? Modulus of Phi is equal to modulus of U P prime. This is an L2 inner product, so you can apply Cauchy-Schwarz. That will give you norm U at L2 into norm Phi prime Phi at L2. So this is given to you. So this is your constant. Yeah, that's this is your constant into Phi prime of U. Okay, so you get this constant norm of U into less than or equal to C into this one if it has a solution. This is true for all phi, any phi. To conversely, assume star. Assume star. Okay, so yeah, assume star, and then you define a space, define W equal to a space set of all P dash of phi. Okay, P dash of phi, where phi is in d omega, and which is a subspace of course this is a easy to check that this is a subspace of L2. Check that because phi is a smooth function, say alphas are all smooth, so these are all things. So you can define now define a linear operator T from W to phi C by, so every element of W looks like a P prime. So it's enough to define T prime of phi for T phi prime by F phi. Okay, for all phi in d omega. For all phi in d omega, P dash of phi is in W. Of course, you have to check the well-definers in the sense that suppose P prime of phi1 equals suppose well-definers. Because suppose to have the two different phi1 has the same thing, you do not know. Suppose phi1 and phi2 gives the same P prime of phi1 and P prime of phi2, you have to show that f phi1 equal to f of phi2. It shouldn't have a difference. So well-definers. That's easy. Well-definers by the condition. Well-definers. If P dash of phi1 equal to P dash of phi2, then you can immediately, that implies you can see modulus of f phi1 minus phi2, apply the inequality given, the star inequality given. So you have this star inequality. So you can apply less than or equal to constant into norm of P dash of phi1 minus phi2. But P dash is linear, so and this is equal to 0. It's linear, so you can apply that one. So this 0 implies f phi1 equal to f phi2. Okay. So that's a well-defined. So that is one point. The second point is T is linear. Okay, immediately, and bounded in that space, because modulus of T of phi prime dash of phi less than equal to modulus of f phi is less than or equal to constant into this is given to you by given condition. This is given. You see, given. Therefore, T from W to C is a bounded linear functional. Bounded linear functional. This is with respect to L2 now. Linear functional. Therefore, by Hahn-Banach theorem, T can be extended. Okay, T can be extended to a continuous linear functional, extended to a continuous or bounded, both are same. Bounded linear functional to continuous linear functional to L2 of omega. Then apply, that implies by Rees representation theorem, there exists U in L2 of omega, because you can identify it with a L satisfying U phi dash of phi is equal to f phi for phi in d omega. That is how you prove the existence. So do that. Okay, so that's also you have proved an if and only if condition, that is pxd of u equal to f, then if and only if u equal to 0. So I will not prove there. So there is a theorem which I will not state here. When pxt is equal to p of d, that means operator with constant coefficients. Operator with constant coefficients then star is true, and hence there is a, this is one example, star is true, and hence L2 existence, for hence L2 existence. Okay, that's all. So this requires a proof. Refer our book. This requires a proof. See the reference. See. Okay. Plus PST. So we'll not do that one, and we'll stop here on this thing. So quickly, in another 10 minutes or 15 minutes, let me go to Sobolev spaces. Sobolev, in context of our early problem, spaces corresponding, we don't mention, so whatever it is. So recall our problem. So recall the problem minus Laplacian of u equal to f. Okay. So maybe little easy to work with. Minus Laplacian of u in omega, u equal to 0 on d omega. A Laplacian of u plus u equal to f in omega. Otherwise, what we require is the Poincare inequality mentioned earlier. Otherwise, require Poincare inequality. Okay. So we will not. So you can use the same thing because of zero boundary condition. So if it's not a zero boundary condition, the Poincare inequality may not be true. So when you deal with these problems with the Neumann and other condition, you have to be a little more careful. Okay. So studying any of these two problems are fine due to Poincare inequality. So what is the corresponding weak formulation? Weak formulation So let me please recall what we have done it in this thing. Weak formulation is grade u, grade v plus integral of uv. If you add that term, so work out even without this. So since we don't have time, we don't want to make further remarks on this. And this should be, so where are we looking at? Initially we have started with u in C1 naught of omega bar, and your v is also there, but you have seen this is not complete, so you have to introduce the norm now. Introduce, this is what we are now. We can be justify whatever we have done in the first two lectures of this series. Introduce a norm of u for this, or norm of v. Okay, so norm of v, let me write it in the square form. So norm of v in this space, this is L2 norm. This norm is different, so maybe I will put one more. That's not necessary. So this norm is not an L2 norm. I'm introducing a new norm. Okay, new norm. So maybe I will introduce new here. Later I will change it. Okay, new norm. This is an L2 norm, and then your gradient norm. That's nothing but your. This is well defined now. du by dxi square. This is already we done. This is nothing but 1 to n. This is nothing but norm of grade v square. This L2. But what we have seen is that C1 naught of omega bar is not complete. And that is why you want to take now completion. Completion is exactly what you are doing now. Completion, this is done earlier. Completion with respect to the above norm, with respect to. So what norms you are taking is very important. Completion with respect to this norm. Okay, then you can actually get this. This is what gives you the first Sobolev space set of all v in L2 of omega with dv by dxi. No boundary condition is used yet. L2 of omega with 1 less than or equal to I less than or equal to n. Okay, and this is called the, and there is a notation h1 of omega, and then this is the Sobolev space. This is one Sobolev space. Sobolev space, and dv by dxi is in the sense of distribution. Now in this, because its L2 functions are, you can define all LP functions are distribution in the sense of distribution. So that's the point. So that's the space you are looking. Okay, in general, not the complete, yeah, C1 naught of omega, but in general we can define. So this is denoted by h1 naught of omega. Yeah, here v is also equal to 0 on d omega. In general, we can define, we can consider without the boundary condition C1 of omega bar with the above norm. With the above norm. Okay, and then you will have then the completion is given by, then the completion is, which will become a Hilbert space, and which we did, completion is some h1 of omega is defined to be set of all v in L2 of omega in such that dv by dxi is in L2 of omega without boundary condition. So you don't pick up any boundary condition. Okay, and of course indeed h1 of not of omega, this is to take care of the boundary contained in h1 of omega, and they are Hilbert spaces with respect to the, and you can extend the same norm, and they are with Hilbert spaces with respect to the norm which we have defined, norm of V nu. Okay, so this is also normally write it as now h1. So both these spaces are Hilbert spaces, h1 naught of omega and h1 of omega, both are kind of some Hilbert spaces which you will need. Okay, so this is the space setting which you do it, and hence you can study, and then once we know h1 naught, so now your weak formulation find u in h1 naught. So you have a formulation now very mathematically stable, gradient of u, gradient of v plus integral of uv is equal to integral of f. You see, and you can get a solution to this problem, so which we already seen that. Okay, so there exists for this, there exists a unique solution u. Okay, and there are regularity results. If you need some regularity of the domain, there are regularity results available. If you have more and more smoothness in HF, you get more and more regularity, and if you have F is very nice, you get back your solutions. You can do all these things. Regularity results are available. There exists a unique solution. Sorry. And you have this and this how Hilbert spaces with respect to that, what we have done is. But then it looks everything is easy. There are difficulties of interpretation still. There are difficulties of interpretation. There are many difficulties. Interpretation. One of the difficulties, so many things, how do we interpret boundary value? How do we interpret boundary values? This is important in a boundary value problem. Boundary values for V in. Though we have written there, there's a problem. There is an issue, or h1 naught of omega. How do we interpret it? Because these are all integrable functions, and the boundary d omega, the reason for this is boundary d omega is a set of measure 0, is a set of measure 0, and hence we cannot restrict it, we cannot restrict V to d omega pointwise, because V is only in L2 or H1, and V is defined on an almost defined as almost everywhere, and so there is no meaning to the boundary values as such right now. So if you start with the function V in L2 or L1, the boundary is a set of measures 0. So whenever, so it's a set with almost everywhere sense. So if you have a continuity up to the boundary, you can restrict. When there is no continuity, you cannot restrict to that. So how do we interpret the boundary value? And these are all very, very serious issues, what are called trace theorems. So to understand trace theorems. The other issues which you have to understand, other issues, this is one trace theorem. The other issue is density theorems. Density theorem. See, most of the time, even though we work with non-smooth spaces, but then you look for that non-smooth functions are an approximations. For example, d omega is dense in L2. It's also dense in with corresponding norms. H1 not. But naturally this is already H1, which is strictly less than H1. You see. So and hence d omega is not dense in H1. Dense in H1. So you need results to approximate. So therefore we need to approximate, because these are all part of analysis, because quite often you have to come to the classical thing to do that. Need to approximate V in H1 by smooth functions. Not necessarily with compact support. With the compact support you can't do it, because you already got all the elements H1 not. Okay, you have H1, so need to approximate by smooth functions. So these are all, it's not very easy, but you need to have this. So this is the calculus you have to develop. Another serious issue, what is called prolongation results. So what you have to expect prolongation. Quite often we need, if f is given, if v is given defined on omega, we need to extend v, to all of omega, all of Rn, because you in full space you will be able to do use other machinery like Fourier transform, etc. So doing analysis in a boundary domain, in a domain with a boundary will be difficult. So you need to extend the domain to without boundary to full domain Rn, and then do the analysis and come back. So you see, suppose V is in L2 of omega, and then you define V tilde, a trivial extension, V in omega and 0 in Rn minus omega. Then by the additivity property, you immediately get V tilde is in L2 of Rn. So you have a trivial extension. This is called a trivial extension. The issue is that this is not true in H1. Not true in general in H1. If you have a trivial extension, that is what I am saying, that if V in H1 of omega need not imply V tilde is in H1 of Rn. So you need non-trivial extensions. Does it exist? Need non-trivial extensions Okay. This is not always true, which requires regularity. Requires regularity in some other form, not necessarily the regularity what I defined earlier. Need requires regularity of omega in some sense. And as a last point, what we call it embedding theorems, which I don't want to tell much here because you need to introduce embedding theorems, because you want to prove whether a weak solution is a classical solution. So the questions what we are asking, can H1, the question is can H1 contained in some continuous functions? Okay, this is a question. Okay, actually what can prove that higher dimensions is true, not true, but when n equal to 1, you can see that for H1 of interval AB is contained in C of AB. So you don't get C, you see H1 means you have the function and its distributional derivatives are L2 in one dimension, that will imply that function is continuous. Okay, so you have C of AB contained in C of AB. Okay, so you get such thing. Need, and there are higher order spaces. There are higher order Sobolev spaces. Spaces HM of omega. There are other LP, there are other LP Sobolev spaces, not necessarily with L2, LP Sobolev spaces. Okay, they are not, you know that only L2 is Hilbert space. Other LP spaces are not Hilbert, so you can define higher order space with respect to P. Such exists. These are all Sobolev spaces when P equal to 2. So you have your, that's your H. And as a final thing, HM in Rn can be defined via Fourier transform. Can be defined via Fourier transform. So there are a lot of literature, lot of analysis, Fourier transform. So I will stop here, and thank you very much. And this completes this set of lectures. Thank you.